In this lesson, I'm going to look at question 7 on the 2019 A-Level Physics paper from AQA. This is paper 1. I'm looking at this question because it really showed that many students had some significant problems in their understanding of electric circuits. This was reflected in the examiner's report, who said that, and to quote, however, big gaps in the knowledge and understanding of electricity were seen in the answers given by many students, end quote. So this is clearly a significant problem for many students, and it's something that I want to address both generally in talking about electricity and then also specifically in looking at this question. So when we look at this question, one of the first problems that many students had was understanding what the question is asking you. Which part of the A-level spec is this question about? And the key word here is practical. What this word practical is telling us is that the cell here has internal resistance. I would suggest for most students that really what you should do is, in any question that shows you a cell in a circuit, assume that there is internal resistance unless you're told otherwise, or unless the question makes it clearly obvious that we can assume that the internal resistance is 0. But in real life, all cells do have internal resistance, so you should start from the assumption that there is internal resistance, unless you can have a reason, a justifiable reason for ignoring it. Okay, right, so we're going to look at internal resistance, and it's one of two circuits that people look at A-level. One is internal resistance, and the other is typically the potential divider. So these tend to be the two main circuits that people are looking at A-level, and both of these circuits can cause students some pain, some difficulty with understanding. But one of the things we can notice is if we look at these two circuits, so if I was to draw a circuit diagram showing the typical situation for internal resistance. So they're saying we've got an internal resistance, small r, some external resistance, and they're measuring the voltage across here. And they might also have shown an ammeter, and they're saying they often put a little dash box around it, and this is our cell. Okay, so that's typically the internal resistance type of question. And then we've got a potential divider question. Here often they tell you that the internal resistance is negligible, and we have something like this. Maybe we have a variable resistor, a second resistor, and we're interested in the voltage across here, and again perhaps we have an ammeter measuring the current. Okay. Now, the nice thing about both of these is both of these circuits are series circuits with two components. So, to understand the operation of both of these, the application of series circuits, which appears in both of these, we need to be sure that we can fully understand how a series circuit with two components can be analyzed. So to be able to do this, we're going to go right back to basics with some really simple questions that we need to be sure that we've understood. So I'm going to ask two questions, which are: what is potential difference? And what is current? And if you'd like to just pause the video for couple of minutes, just try and think up your definition for these two quantities, what it is you would answer. Okay, so let's take a look at potential difference first of all. So potential difference is the work done or energy transferred on the charges. So in moving a unit charge between 2 points in a circuit. Now, what does that mean? So if we think of a really simple type of circuit, here we have a cell. Again, I'm assuming that there is no internal resistance, and I have a lamp. So what's happening here is that the electrons, which are our charge carrier, are drifting around the circuit. As they pass across between this point and this point, we have a voltage or a potential difference, and the potential difference here is equal to the energy transferred per unit charge from the cell to the charge carriers, in this case the electrons. There's another way that we describe this. Instead of calling this potential difference, it has another name, the electromotive force, or EMF. Okay. And then what happens is the electrons go around the circuits. They're then going to transfer their charge to this lamp. So again, if we measure the voltage or potential difference across this lamp, here the potential difference is equal to the energy transferred per unit charge from charge carriers, which are the electrons, to the component, in this case the lamp. And I think it's pretty easy to see that if everything was ideal, we do not have any internal resistance in the cell and the wires are assumed to have zero resistance, then whatever the potential difference is here, that is equal to the potential difference across the component. Why? Because all the energy that's given from the cell to the charge carriers is transferred to the component. So we can say that, to summarize this mathematically, we can say that the voltage is equal to the work done in moving the charge carriers from this point to this point. So we have the potential difference is the work done, and we have the EMF is equal to, which is this one, is equal to the energy transferred to each of the charge carriers per unit charge. And in this case, these are the same. Okay, so let's take a look at what current is. So current is the rate of flow of charge. And so we can write that mathematically as the current is equal to how much charge has flowed past a particular point in a certain amount of time. Okay, so we have that the current is equal to the rate of flow of charge. Okay, so let's take a look at how we can use these ideas of current and potential difference to analyze the circuit. So in some ways we can think of circuits as essentially machines that transfer energy from one place to another, in this case from a cell to some sort of component. That transfer is happening at a particular rate given by our current, and we can analyze the circuit, how it behaves, using the ideas of potential difference and current. So these ideas were formulated as laws by a man called Kirchoff, and he came up with two of these laws. So first of all, we can talk about Kirchoff's current law. And Kirchoff's current law is based very simply on the idea of conservation of charge. So if you imagine inside a circuit, I'm going to show it as a simple parallel circuit with two resistors. Okay. Now there's a certain number of electrons inside these objects, and that number of electrons won't change when the circuit is operating. And because the number of electrons doesn't change, then the number of charges won't change, because the charges are on the electrons. So from conservation of charge, we expect that whatever happens inside this circuit, we can't add charge, or we can't take charge away just through the operation of the circuit. Okay, so once the circuit starts to work, what will happen? So we're going to switch on our circuit, and we have a current flowing, and it flows through these two components and the back around the cell. Now, from conservation of charge, we're interested in this case in seeing what has happened at this point. So let's zoom in and take a quick look at what's going to happen there. So what I've got is this current, I'm going to call I1, this one, which is some sort of value I2, and this one, which is some sort of value I3. Okay, so how can we relate I1 to I2 and I3? So from conservation of charge, no charge is lost or gained at this junction. That's what the conservation of. So if, for example, in 1 second, 6 coulombs of charge was flowing in from I1, then 6 coulombs of charge every second must flow out via I2 and I3. So that means that I1, whatever current I've got in I1, must be equal to the current in I2 plus the current in I3. So we can summarize that by saying that the sum of all the currents that go into any junction must equal to the sum of the currents coming out of the junction. That's Kirchoff's current law. And Kirchoff's voltage law. These, by the way, are sometimes called the first law and the second law. This is based on the idea of conservation of energy. So that gives us a clue that this is going to be about potential difference and EMF. And here what I'm saying is, and we look back at our very simple circuit that we saw where we had a cell and a lamp. This is saying through the operation of this circuit, the energy that's been transferred to the charge carriers, it cannot be created or destroyed. We cannot add any extra energy through the operation of this circuit, and we cannot make any of the energy disappear. It can only be transferred from one form to another. So since energy is conserved, that tells us that the total amount of energy that's transferred from the cell to the charge carriers must equal the total amount of energy that was transferred from the charge carriers to any of the components, so that no energy has been created and no energy has been destroyed. So here I've got one value for the EMF, and I've got one value for the potential difference across this component, and they must be equal. Now, in general, we summarize this by saying that the total EMF in a series circuit, or more generally, we can just say in a loop, must be equal to the total of the potential differences across all of the components inside that circuit. So that's Kirchoff's voltage law. Now, interestingly, for anyone who might go on to use electric circuits, particularly build them or use them as engineers, these two laws form the basis for most circuit simulation software that's used. The most well-known one is a software called SPICE that's used for circuit simulation, and that, for example, that uses Kirchoff's current law to do all the analysis of complex circuits to work out what are the current flowing through each part of the circuit, and hence what the potential difference is at any point in the circuit. So we can use these two laws to analyze any particular circuit that we might be interested in. Let's go back to question 7 and look and see how we can use our understanding of electric circuits to analyze this circuit in order to be able to answer the question that we've been asked for part 1. Now, we're told in the question that a variable resistor is used to control the brightness of the lamp. Okay, so it's the variable resistor that's controlling the brightness of the lamp. So when in question 1 it says, explain why the reading of the voltmeter decreases as the brightness of the lamp increases, we know that this is because of some change in the variable resistor. We are changing the variable resistor somehow, either increasing or decreasing its resistance in order to make the lamp brighter. Okay. Second thing I'm going to think about is I now know that this should have internal resistance here. So I'm going to just redraw my circuit just to make sure that I've fully understood what exactly it is that I'm looking at. So if I was to redraw this circuit, what I had was, I had a circuit that looked like this. I had the variable resistor and I had my lamp, and here was my voltmeter. But we need to show the internal resistance, and internal resistance normally drawn like this. But I'm going to change this diagram ever so slightly just to make things as clear as I possibly can. So I'm going to just move the internal resistance down here. Here's my variable resistor. Here's my lamp. And remember, I'm measuring the voltage across the lamp and the variable resistor. Okay. Right, so when we look at this circuit, we've got a certain number of volts for the EMF here. I'll just call that E. And then we've got three components. We've got the internal resistance, we've got the variable resistor, and we've got the lamp. Okay, now looking at Kirchoff's laws, Kirchoff's current law, okay, the analysis of the current is relatively straightforward here. It's a series circuit. We can assume the voltmeter is very high resistance, so no current is passing through the voltmeter. Therefore, the current is always the same. So at any point in that series circuit, the current is always the same. So wherever I measure it, I will always get that value for the current. Okay. Looking at Kirchoff's voltage law, so that's telling me that the EMF from my cell, it's equal to the sum of the potential difference across each of these components. So I've got I times the internal resistance, which is the potential difference across this component, plus I times the variable resistance, plus I times the resistance of the lamp. Okay, now I'm going to slightly reword this equation, rewrite it so that we have the EMF is equal to potential difference across the internal resistance plus the potential difference that's across both the variable resistor and the lamp. Okay, now we can just think a little bit about these resistance values. This resistance value for the internal resistance, this won't change. We can for the moment ignore any change in the voltage due to heating effects. This one also won't change. So really what we're thinking about, because the question is asking us why the reading on the voltmeter decreases, we're seeing why will this value, why will it change, in this case decrease. So there's only two possibilities here. The current decreases and this changes. So these are the only things that can change inside this circuit. Okay, so if we write that out again, we have the EMF is equal to the potential difference across the internal resistance plus the potential difference across the variable resistor and the lamp. Now we're told that the brightness is increased. So for the brightness of the lamp to increase, the variable resistor was adjusted to increase the current. So we're going to increase the current that goes through the lamp in order to increase its brightness. So we're going to increase I. Now to increase I, what we need to do is we need to make sure that we have lower overall resistance. So it's a series circuit. The total resistance is equal to resistance of the internal resistance plus resistance of the variable resistor plus resistance of the lamp. And we can see that from our equation above, that's going to give us a value for all of this is equal to E multiplied by I is equal to the EMF. Now I want to get a larger value for I, so I is equal to the EMF divided by the total resistance. So to increase I need to decrease RV. So I'm going to decrease RV, and that will, because the other two resistances can't change, so that will give me a larger value for I. That will cause the lamp to increase in brightness. Having arrived here, it can seem confusing to some students, the fact that we have increased the current to make the lamp brighter, but we're saying that the voltage that we're measuring is going to go down, because we're used to the idea that voltage is equal to current times resistance. So we need to think about looking at Kirchoff's voltage law, which has given us this expression, how this voltage is shared between the internal resistance and the components that are external. So to understand this, let's think of a simple example first of all. So imagine I have a series circuit where I have two resistors. One is 1 ohm, the other one is, let's say, 7 ohms, and there is 8 volts of EMF. Okay, so we can say first of all that the total resistance is equal to 8 ohms. That means that the current, which is equal to the voltage divided by the resistance, is equal to 8 volts divided by 8 ohms, which gives me a current of 1 amp. So from Kirchoff's voltage law, we know that that voltage of 8 volts is going to be shared between the current times R1 and R2. So current times R1 plus current times R2. In this case, R1 is 1 ohm, R2 is 7 ohms, and the voltage is 8 volts. So that means that the potential difference for the first resistor is 1 multiplied by 1, which gives me 1 volt, and the potential difference across the second one is 1 multiplied by 7, which gives me 7 volts, and when I add those together, I get 8 volts as given by Kirchoff's voltage law. If, however, now I was to keep this resistor the same, but now make this resistance smaller, let's say 3 ohms, now my total resistance has been reduced. That means that the current is increased. And again, I can look at the potential difference across each of these. So across the first one, I've now got 2 multiplied by 1, which gives me 2 volts across the first one. And across the second one, I've got 2 times 3, which is 6 volts. Again, those add up to give me 8 volts, as required by Kirchoff's voltage law. But we can see that the voltage has decreased. So in the case of our example, what we are interested in is the voltage that is across the variable resistor and the lamp. And because I've decreased the resistance of the variable resistor, the resistance of this combination of the variable resistor and the lamp will decrease, while this one stays the same. So in the same way as we showed in this example, the potential difference across this part will become smaller. So let's go back to our question and see how we can answer that. So in answer to my question, well, I'm going to start by saying that the cell has an internal resistance so when current flows, there is a potential difference across this resistance. Now we can say that when the current is increased, by reducing the resistance of the variable resistor, the potential difference across the internal resistance increases, so the voltage in voltmeter decreases. You could also answer this in terms of saying that because the resistance of the variable resistor decreases, then the internal resistance makes up a larger proportion of the total resistance of the circuit. That would also be an equivalent way of saying, of answering this question, an equivalent way of saying the same thing. Okay, so in the second part of the question, they say that the variable resistor is adjusted so the lamp is at its brightest. So we're going to set this variable resistor to some value, and it's not going to be changed at that point. The reading V1 on the voltmeter is noted, and they then say that they add a second identical cell in parallel with the cell as shown. And they say that there is a new reading V2 on the voltmeter. And we need to try and explain why is it that the new reading on the voltmeter is larger. In other words, the voltage across the lamp and the variable resistor is going to increase when we add an additional cell in parallel. Let's take a look at a little bit of what happens when we add cells in parallel. So again, I'm going to start from something that's pretty simple. Here I have circuits. Again, I'll make it a lamp with a cell. Let's say this lamp is 10 volts. Let's say, for convenience, that the resistance of this lamp is 10 ohms. Sorry, the EMF is 10 volts and the resistance of the lamp is 10 ohms, which means that then our current is going to be 1 amp. Now, if I place another cell in parallel and like this, I'm going to assume that there is no internal resistance initially. Let's take a look at what Kirchoff's law tells us about this. Now, we're looking at voltage in this case, and in the Kirchoff's current law, or Kirchoff's voltage law, remember it says that the sum of the EMFs is equal to the sum of the potential differences. So in this loop, if we look at this one, first of all, going from A to B to C to D, first of all, we've got 10 volts for the EMF is equal to the voltage across the lamp, which is 1 times 10. So that's correct. Then we've got this larger loop, so let's make that EFCD. So we're going to ignore this part for the moment. And again, what that shows us is we've got 10 volts is equal to 1 times 10. That's the same. And then we've got the final one, which is this one. And interestingly, we don't have any value for potential difference here. There is no component. But you'll notice that the cells are the opposite way around. So the plus side of this cell is connected to the plus side of this cell. So what we have is 10 volts minus 10 volts, which equals 0, which is correct. So if we have theoretical components with no internal resistance, adding the second cell in parallel seems to have not really very much effect. The only effect really that we can say in this case is if we look at Kirchoff's current law, and then we see that here we have a junction, then these two currents added together must equal this overall current of 1 amp. So each of these, since I equals 1, I1 equal to I2 is equal to a half an amp. So the only advantage shown in this case of adding the extra cell is that the current through each of the individual cells is reduced. So we might argue that because what the cell does is it transfers energy, we could argue that the cell lifetime might be longer because the rate of flow of charge carriers through the cells is reduced. Okay, but we're going to now think about this in slightly different terms in case of where there is an internal resistance. We're going to assume that the cells are still identical, so the internal resistance is the same. And we're going to see what would this mean in terms of what happens to a circuit. So again, we've got 10 volts for the cells, for the EMF. Now we've got an internal resistance of 1 ohm, and we've got this external resistance of 10 ohms. So if again I look at Kirchoff's voltage law, what I have is for this loop, I've got 10 volts of EMF is equal to the current that flows through this one, which is I2 from my I1, I2, and then I've got the total current plus the current flowing through this 10 ohm resistance externally. And likewise, I have the same thing for the larger loop. It's going to give me the same expression. Let's go to I1 times 1 ohm. And then I've got the final one, which is going to be the same as before, where I've got 10 volts minus 10 volts is equal to I1 times 1 ohm here minus I2 times 1 ohm there. And again, this would be 0, and that assumes, so this is 0 if I1 equals I2. And we said they're identical, so we can assume that's correct. Now, remembering that I is equal to I1 plus I2, and that means that since these are the same, I could rewrite that as I is equal to twice I1. Then using this equation, I can say that 10 volts is equal to I1 plus 20 times I1. Okay, so using this, then I can calculate a value for I1, which is 10 divided by 21, which is going to be a value of I1 is equal to 0.48 amps. Therefore, my current is equal to twice that, 0.95 amps. Okay, now the voltage then drop across my lamp, whereas in this case the voltage drop was 10 volts, where we had assumed no internal resistance. The voltage drop across the lamp is now going to be equal to 0.95 times 10 is equal to 9.5 volts. So I've lost a half a volt in my internal resistance. Right. Now we need to just compare this to what would the situation be like if I only had one cell. So here I have my lamp and one cell. Again, it's providing an EMF of 10 volts. Our resistance, I said, was 1 ohm, and this is 10 ohms. So a lot easier to analyze. In this case, the total resistance is equal to 1 plus 10 is equal to 11 ohms. Therefore, I is equal to V divided by R. Gives me I is equal to 10 volts divided by 11 gives me the current is equal to 10 divided by 11, which is 0.91 amps. So again, look at the voltage or the potential difference across the lamp. It's equal to I times R, so that's going to be equal to 0.91 times 10. This V is equal to 9.1 volts. So here I have 0.9 volts lost. Whereas previously I said if I had had two lamps in parallel, 0.5 volts lost. So what this analysis has shown us is that by adding an extra cell where I have an internal resistance, I end up with less voltage being lost through the internal resistance. In this example, where I had one cell, I lost 0.9 volts. When I have two cells, I only lose 0.5 volts. Another way to think of this is that the internal resistances are being added in parallel, and what we know is that when we add resistance in parallel, the total resistance is smaller than any one of the values that are in parallel. And we could work that out using the usual formula to work out the value for the total of that parallel internal resistance. And again, that will show us that we have an equivalent internal resistance, meaning that we get 0.5 volts lost. So coming back to our question, and remember we said that none of the resistance values change. All that changes is that we add this additional cell. This additional cell has got the same internal resistance. That means that we have these two cells will act as if it was one cell with a smaller internal resistance. So because there is smaller internal resistance, there are less volts lost across the internal resistance, so there is more voltage across the external components. So you have a choice on how to answer this question. You can either answer it in terms of the voltage lost, or you can answer it in terms of the equivalent resistance for the two cells in parallel. Okay. The third way to actually answer this would also be in terms of the current. Okay, right, so explain why V2 is greater than V1 when a second cell is added in parallel. The two cells behave as a single cell with the same EMF but reduced internal resistance. As the internal resistance is reduced, fewer volts are lost because of internal resistance. So the reading in the voltmeter increases. Okay, and that was question 7. A tricky enough question. The thing to remember, as I said at the start, is always assume that there is internal resistance in cells unless you're really sure that you're justified in assuming that the internal resistance is negligible. And the second thing to remember is that both of these circuits, the internal resistance EMF circuit and the potential divider circuit are both forms of series circuits, generally speaking with two components. So long as you are confident about how to analyze a series circuit, you should be able to answer any of the potential divider circuit questions or any of the internal resistance questions without too much difficulty.